Hello everybody, today I will talk about a topic about the Chebyshev inequalities in measure theory. So let's start our video today. So I'll start from introduction, which these are some notation we will use in the following slides. And first is the measure of a set E, we will write into this form. And also the Lebesgue integral, where f is a function which is measurable, and also E is a measurable set in Rn. And next is the set of f larger than a. We define it as the wherever the x in the E, the measurable set E, such that the fx is larger than a. Okay, so we'll first look into what is the definition of Chebyshev inequality. And the theorem is that below, which is let f be non-negative and measurable on E, which this E is a measurable set. Then for all a larger than 0, we can write it as the following inequality. And a sketch or proof is as following. And we can see that the purple line is the function of the f, and we define a, which is this green line, and we can find out that the set for f larger than a is from this point to this point. So we can easily see that the area of this highlighted is definitely smaller than the area under the function f. So which means that these inequalities will hold, because this inequalities is an a times the length of the set where fx is larger than a. So this is definitely the area of this highlighted set, highlighted area. And the Lebesgue integral of f is the area under the graph of f. Yeah, so in this simple graph, we can see that the inequalities will hold, and this inequality will hold for all a larger than 0. So let's do a rigorous proof of this inequality. And since that we know that the function f is non-negative, so it's larger or equal to 0, and also the set f larger than a is inside the E, because we can see that from the previous from here, if we let the E to be, let's say this is 0 and this is 1, so we can see that if we set the E to be 0 to 1, then the set that f larger than a will be inside this interval too. So we can see that the set f larger than a will be also inside E too. So we can these two, and we can have that a times the measure of the set f larger than a will be equal to the Lebesgue integral of a on the set f larger than a, which is definitely what I said just now, which is this, the area of this highlighted. And from this we can easily see shown that it's smaller than equal to the Lebesgue integral of f on the set f larger than a. Also, this one can be easily shown by the graph, these two, because you see that when we are on the set of f larger than a, then this area under a will be smaller or equal to the area under the f. So yeah, this inequality holds, and from this we can further see that E is smaller or equal to the Lebesgue integral of f on E. So this is similar than what I said just now. We can see that the area under the f, if we just consider the set f larger than a, is just from this onwards. But if we see that for all E, then it will include all the points which is not in the f larger than a too. So it will definitely be larger or equal to the previous one. So, and this will end our proof of this Chebyshev inequalities. And where does these inequalities are useful? we can see that it can be used in some theorems, some other important theorems. And let's show an example of a theorem that use these Chebyshev inequalities. So this theorem is we let the f be a non-negative and measurable function on E, which is similar as just now. Then the Lebesgue integral of f on E is equal to 0 if and only if fx equals to 0 almost everywhere for x in E. So f equals to 0 almost everywhere is like the f is only not equal to 0 for a major 0 set. So we can remove all the major 0 set, which is not much important to us. So we said that the f equals to 0 almost everywhere. And for this theorem, we will provide the proof too. So the easy part is from the right to left side, which is if fx equals to 0 almost everywhere, then the Lebesgue integral of f equals to 0. So we first let the set z equals to the set of fx not equals to 0. And because we said that f equals to 0 almost everywhere, so this set will have a major 0 set. And thus we can write the Lebesgue integral of f on E equals to the Lebesgue integral of f on E minus z plus the Lebesgue integral of f on z. And we know that the z has measure 0, so 0 times any function will be 0. And the E minus z is the function where f is 0. So because we remove all the non-zero part which is in the z, so this f will be only 0 everywhere. So integral of 0 will be 0, then 0 plus 0 will also equal to 0. So we prove that if fx equals to 0 almost everywhere, then the Lebesgue integral of f on E will be equal to 0 too. And next, from left side to right side, here is where we will use the Chebyshev inequality. And we can first see that for any a larger than 0, the Chebyshev inequality holds, and this part equals to 0 as a theorem set. So with this, we can see that because the a will be larger than 0, so this measure of the set f larger than a will be equal to 0 for all a. And because this will be for all a, then we can write it as the measure of the f larger than 1 over k will be equal to 0 for all k in the positive integer too. After we write to this one, then we can easily see that for the measure of the set f larger than 0 will be smaller or equal to the sum from k equals to 1 to infinity of the measure of the set f larger than 1 over k. So we will easily see that this one will be equal to 0. So the measure of the f larger than 0 will be 0. And because of the measure of the set f larger than 0 is equal to 0, and also that the f we let it as a non-negative function, so we can easily prove that the f equals to 0 almost everywhere if the Lebesgue measure of f on E is equal to 0. And this ends our proof, and we'll look at. And lastly, we will look into the other version of the Chebyshev inequalities. So on the top, I put the definition of the Chebyshev inequalities that we proved a few minutes ago. And we have another version if you have learned about the LP space in measure theory. We can also use these Chebyshev inequalities in the LP space. So it's somehow similar. The definition is that let f be a non-negative and measurable function on E, then for all epsilon larger than 0, the inequalities holds for all 1 smaller than equal to p smaller than equal to infinity 2. And this ends our video today. Thanks for watching.